going to be doing question number 3 of homework chapter 29 and 30. And let me start by reading the question. Part A. A long solenoid has a cross-sectional area of 3 centimeters squared. The current through the windings is decreasing at a rate of 22.0 amperes per second. A wire loop of radius 3.10 centimeters is around the solenoid parallel with the coil and is centered on the axis of the solenoid. The magnitude of the induced EMF is 15.0 microvolts. Find the number of turns per meter in the solenoid. So I'm gonna try my best to draw the solenoid. I'm not really good at drawing, so let me try my best to do the solenoid. Okay, I think okay, so I think not really good at drawing, so I'm gonna try my best. Okay, so I'm gonna label. Okay, so this is where the A is. Okay, so a circular wire loop around the solenoid. So okay, this is the best way I can do it. The circular, so it's going around basically. And that's the cross-sectional area. Which is let me write it. Oh no. Okay. Yes, so I'm gonna label it 3.0 centimeters square. That is the cross-sectional area, and then I'm gonna label the current. So the current would be, I believe, just gonna label it here. It's a current at I, and then I'm gonna write the GRDT, which is this is the current through the winding is decreasing at a rate of 22 decreasing, so it's gonna be negative 22 amperes per second. And then we're gonna label the induced EMF, the electromotive force, which would be not good at drawing, but just gonna microvolts. Okay, 15.0 microvolts. So we have to find the we're trying to find the turns, like how many find the number of turns per meter in the solenoid. So let's do that. Okay. Okay, let's start with the magnetic field equation. So let me just explain this diagram real quick. It's not the best, but the current in the solenoid basically is decreasing, and the changing current produces a changing magnetic field. And according to Faraday's law, a changing magnetic field induces a electromotive force in the surrounding loop. So let's let's write the magnetic field equation now. And so inside the long solenoid, it would let me write down the equation first. and I'll explain it. Okay, there you go. So this is the magnetic field inside a long solenoid. So B is the magnetic field in Teslas. The mu naught is the permeability of the free space. So it's basically a physical constant, and also N here is the number of turns per meter. So this is what we're trying to find, and I is the current through the solenoid. So now we have to write the magnetic flux equation. So the magnetic flux is, let me write the equation here. Okay. This is, oops. Let me put that in. Okay, so this is P sub B, which is the magnetic flux. B is the magnetic field, and A is the cross-sectional area of the solenoid. So we have to substitute the magnetic field equation. So what we're doing is this B right here, we're basically substituting it into this equation to make a new equation. So that would be the magnetic flux equals to number of turns, the current, and the dA, which is the area, the cross-section area of the solenoid. Okay, so now we're going to apply the Faraday's law. In Faraday's law, it states that the induced electromotive force is equal to the rate of change of the magnetic flux. So let me write that real quick. The induced electromotive force equals to the rate of change in, in the, hold on, that's not good. Yeah, so that's the rate of change of the magnetic flux. So let me explain this equation real quick. This is the script E, induced electromotive force. This is the D, which is a very small change. And this is the DT, which is a small change in the time. So, and then over here, so basically this whole thing means the rate at which the magnetic flux changes with the time. Okay, since only the current changes, hold on. Since the current only changes, we're going to do not turn the number of turns, the area of the cross-sectional area, and the okay. So this is since the current only the current changes. So okay. So now we have to solve for n. So let's take the n out. Okay. Basically, we just put this over here, up here, and the I, because and the I only because the current is changing, so that's how we equal to. So we're solving for n. So let's isolate the n by dividing both sides by. So basically, if we isolate the n, we have these are all multiplied to the n. So we're gonna have to divide it to the other side, which is gonna give us oh, oops, I made a mistake. Okay, this is this is equal to the number of tens. Okay, so now we have to convert the units. So now we can start putting everything into it. Okay, let's do that. So we know that the EMF is 15.0 microvolts. So let me just put it here. So that's gonna be 1.50 times 10 to the power of. Oh, sorry, I made a mistake. We're actually converting the EMF. So so basically we're just gonna substitute it 2 volts. 15.0 times 10 to the power of negative 6 volts all the way over. Okay, so the mu naught, hold on, so the value of mu naught is, 4 pi times 10 to the power of negative 7. So hold on. Yeah, so the mu naught is equal to 4 pi times 10 to the power of negative 7 WB times A over M. Let me just double check. Just to rewrite it here a little bit. Mu naught is equal to 4 pi times 10 to the power of negative 7. I think you, hold on, I'm just checking the textbook to double check. It's MB divided by A times M. I just didn't want to make a mistake. Okay, so the WB is the Weber per ampere meters. So I wanted to double check if I got the formula correct. I didn't want to make a mistake. And so where was I? Okay, so once you know that, we're going to do 5 so now we have to find the A, which is the cross-sectional area, which we know is 3 centimeters squared. So to convert the area, that would be 3.00 times 10 to the power negative 4 meters squared. Yeah, that's right. Okay. And then now we have dl over dt. This is the current through the winding is decreasing at a rate, so of negative 22.0 basically. Okay. So now we're gonna calculate everything to find the n, the number of times. So let me get my calculator. So okay. Okay, so around the top, I got 1,810. So hold on. Okay, so I got the number of turns per meter 1,810. So therefore the number of turns per meter in the solenoid is 1,810 turns per meter. So that is the answer for part A. Okay, now we're gonna be using the same diagram and the same values, but now we know the n of number of turns. I'm gonna write it down here. N equals to 1,810 turns per meter. Okay, gotcha. Okay, so now for part B, find the magnitude of the induced electric field within the loop. So we did this in the textbook, I believe, in the chapter 29.11 example. And so we're gonna. Okay, so this is so hold on. I'm not really. So we're trying to find the magnitude of the induced electric field in the loop. So this is gonna be my best drawing, or is based off of this. Okay. Okay. This is the magnetic field. I think. Hold on. Let me think how I would have to draw this. That would be magnetic field, and then so. I don't remember how to draw it, but magnetic field of the induced electric field within the loop. So the loop is like going like this around basically, and it's like going basically like this, like that, and it's gonna be the side of these each, and this E is basically the electric field vector on top. So it's basically telling us the direction this way, and the current, I believe, is gonna be going this way. Yeah, so that's the best way I could describe it. So like this is like the changing the magnetic field, basically like induced the electric field that like basically forms like a circle around the solenoid. So we also know the radius. Yes, the radius is, I think I forgot to write it up here. So the radius of the loop is 3.10. Okay, so the radius that is 3.10 centimeters, which we knew from the last part A. So we have to let's convert it to meters, which is gonna be 0.0310 meters. Okay. So we're gonna write the Faraday's law like it was in the textbook, which, hold on, let me write it down here. Let me bring this down here so we don't get confused. And let me label this. This is part A, and this is part B. Okay. So let me write the law, and then I will explain everything. let me explain. So this is the closed line integral around the loop. This is the electric field. We're multiplying it by dl. I believe this is dl. And I think that was the small. The d is a small piece of the loop. So this is the rate of change of the magnetic flux, which is hold on. So since the loop is a circle and electric field has the same magnitude everywhere across the loop, like that I wrote here. Here. But so the closed line integral around the loop electric field times d. That's one equals to electric field times 2 pi r. And since the EMF is equals to E2 pi r. I think that was in the textbook. So we go right here. So that's the right I wanted to show in the textbook as well. And so then the electric field is EMF 2 pi r, like I showed in the textbook. So this is the induced electric field, induced EMF, electric metaphor. This is 2 pi r. The 2 pi r is the circumference on the circular loop, and we know that the r is the radius. So I'm dividing the induced EMF by the circumference because the electric field is basically spread like all over the entire loop. So let's start by converting the EMF that we know. Oops. Sorry. EMF. I'm gonna write everything down over here. So. Okay, so we know that the EMF in the part over here is 50.0 microvolts, but we're gonna convert it to volts times -6 volts. Then we have 2 pi, and then we have r, and r is 3.10 centimeters, which we converted to meters. So yes, 10 meters. Okay, so now I'm gonna calculate it in the calculator. -6 divided by 2 pi times. Okay, and I'm going to round it, and it's gonna give me 7.7 times E to power -5 volts per meters. That would be. This is the answer for part B. Now we move on to part C. Let's read it. Oh, hold on. Let me. Sorry. So for part B, the magnitude of the induced electric field is within the loop is 7.70 times 10 to the power negative 5 volts per meter. Okay, so now we're going to do part C. Let me read the question. A circular wire loop of radius 0.360 centimeter lies in the XZ plane. There is a uniform magnetic field in the y direction that decreases at 0.0150 Teslas per second. Find the magnitude of the induced electric field in the wire. So, okay. So, I'm gonna draw the cross section of the solenoid. So I'm just gonna draw a circle. So it's just more simple to understand. Okay. Parts. Okay. Red, orange, and this is. Let me make it more thicker so it's easier to see. So this is the point. Then when this is the point, that okay. So I think how would I explain this? The radius, I'm gonna draw like that. 0.260 centimeters. Okay, so I'm not really this oxygen plane. Just go here and oops. Okay, so I'll make more. Okay, so we know that the uniform magnetic field dB/dt and if you're in the y direction decreases at 0.0150 Tesla per second. That's the time. So that's all we know. To find the magnitude of the induced electric field in the wire. So the dot here represents the center of the solenoid, and then the small arrow from the center of the point is the radius. And the curved arrow, I try my best, is the electric field I try to show. Like here and here. Okay, so now that we did that, how would I explain it? Okay, so the magnetic field inside the solenoid is basically increasing at with time. I think it's decreasing actually. Hold on, give me a second to think. Sorry, I made a mistake. I saw it said increasing instead of decreasing. So it's okay. So it's gonna be negative. Negative, and this is actually gonna go. Okay, this is the best way I can explain it. Okay, so I actually made a mistake. So the point where I need to find the electric field is 0.360 centimeters. And the magnetic field is decreasing at a rate of 0.0150 Tesla per second. So an induced electric field forms in a circular loop. It would be like this, like that looking. No, I'm not. Yeah, it would basically go this. I think put it this way. Yeah, this way. Okay, so an induced electric field is going to form in a circular loop around the axis of the solenoid. Okay, so we're going to be using the Faraday's law, like we did in the last part. Closed line diagram, the loop, induced electric field, it is part of the circular path, the loop. If we go to negative okay, so let me explain it. So this is the closed line diagram and the loop. Induced electric field times the small piece of the circular path, and then it's going to equal to the phi sub b, which is the magnetic flux, over dt. So this is basically the rate of change of the magnetic flux, and it's gonna be negative because so which basically, since the electric field has the same magnitude everywhere on the path, which we know, it's so the line of like the integral basically means that the electric field is multiplied by the circumference of the circle. So let me explain. Equals to E times the circumference of the circle. Okay, electric field times the circumference of the circle. I'm gonna write the magnetic flux, which we know is magnetic flux is equal to the magnetic field multiplied by the area enclosed with the circular path. So now we are going to do is we're going to differentiate with respect to time. So that's going to be so what we did here is we okay. So the dB is the small change in the magnetic field, and the dB over T is the rate of change of the magnetic field measured in Tesla per second. Okay. Now we're going to substitute into the Faraday's law, which is let me use a different color. So since the problem is asking for the magnitude of the induced electric field, induced electric field, I use the magnitude of the rate of change of the magnetic field. The fact that like the magnetic field is decreasing is gonna affect the direction of the induced field through the Lenz's law, but it's not like but not by its magnitude. So we're gonna cancel the pi and divide both sides by 2r, and that's gonna give me E equals to r over 2 so divided by 2r, and it's gonna be okay. So that's the new formula. So we're going to convert the radius now, which is 0.360 centimeter into meters, so 0.003 So I'm converting the centimeters to meters because all the quantities should be in SI units. So now we're substitute the values into. So E equals to 0.00360 meters. Divide that by 2. And dB over dt is, as we know, is decreasing by the 150 times. Let me put everything in the calculator. 0.00360 divided by 2. And I got 2.7 e negative 5. So let me write it down. 2.70 times 10 to the power negative 5. Okay, watts per meter. Okay, so that is my answer for part C. The magnitude of the induced electric field in the wire is 2.70 times 10 to the power negative 5 volts per meter. And also I want to explain the reason why I put a negative here is to show that it's decreasing. It helps me remember it better. But when we put it in the Faraday's law, okay, so let me explain. So the reason why the reason is that like the problem is asking for the magnitude of the induced electric field, and the negative sign in the Faraday's law right here, which is EMF that is the Faraday's law, and so it comes from the Lenz's law, which tells us that the direction of the induced field. But since we're only finding the magnitude, you're gonna use you have to like find the absolute value. That's use the absolute value, so it's gonna be no negative sign. Okay, now we're gonna do part D. It's in part D, right? Yes, part D. Which is a separate question. Part D. Okay. A long solenoid with a cross-sectional area of 4.00 centimeters squared and 965 turns per meter is oriented with its axis along the z-axis. The field inside the solenoid points in the positive z direction. The wire loop of the radius 5 centimeters is around the solenoid parallel with its coil centered on the axis of the solenoid and lying in the xy plane. Find the rate of change of the current in the solenoid if the electric field in the loop at the point x equals to 5 centimeters, y equals to 0, z is equal to 0, is the electric electric field is equals to positive electric field is equal to positive 1.20 times 10 to the power negative 5 volts per meter. Volts per meter. Hold on. I think I forgot. Wait, so let's read the question again. A long solenoid with a cross section of 4 centimeters squared and 965 turns per meter is oriented with its axis along the z-axis. The field inside the solenoid is positive z direction. A wire loop of radius 5 centimeters is around the solenoid, parallel with its coil, centered on the axis of the solenoid in the lying in the xy plane. Find the rate of the change of the current in the solenoid if the electric field in the loop at the point x equals to 5 centimeters, y equals to 0, z is equal to 0, is electric field is equal to 1.20 times positive 1.20 times 10 to the power negative 5 volts per meter J hat. So it's in the basically it's in the positive y direction. So let's draw the diagram. The best way is okay. The best way I'm gonna draw is I'm gonna draw like a top view of like on the XY plane. So so I'm gonna do is okay. I'm gonna draw a point right here. Positive y, this is the positive x. Equals to positive j. Okay. We know that the number of turns in numbers rectify. The cross section is 4 centimeters squared. Radius is 5 centimeters, and the B it points out basically in the positive. The B is the electric field in positive. Okay, so so let me explain. The solenoid magnetic field points in the positive z direction, which is out of the page, and the electric field at point P points in the positive y direction. So that's the best way of how I could explain in my diagram. So I'm going to be using Faraday's law. So let me write it right here. I'm going to use this color green. Okay. So I'm using Faraday's law because the changing the magnetic field inside the solenoid induces an electric field around the loop. So this so let me explain. So basically this symbol is the closed line interior around the entire loop. This is the induced electric field. This is the small piece in the circular path, and then V sub B. This is the magnetic flux. So this whole thing here means the rate of change of the magnetic flux. Okay, so because of electric field is like the same everywhere around the loop, we know that as we know, it's electric field times 2 radius. So since the electric field has the same magnitude everywhere on like the circular loops, the line integral becomes an electric field multiplied by the circumference. So now we're gonna write the magnetic flux like we did before, which is B times A, the magnetic field times the area. So we already know from the last parts, so I'm not gonna rewrite it. I'm going to, since I already explained it before. So it's gonna be, so we basically substitute and then we differentiate with respect to times. So okay, so only the current changes with time, so only the I is differentiated basically. Okay, so now I'm going to plug everything together, and we're solving for so this is actually okay. Where was I? Oh yeah, so this is gonna be, so we're gonna solve for the I. We're finding the rate of change in the current. So di2 is equals to 2 pi r over 3. So we're substituting into the Faraday's law, which would have been electric field times the circumference equals to the mu naught the number of turns, area, and this is the rate of change in the current, which we are trying to find. So I substitute everything out, and this is the equation I got left up with. And now I'm gonna plug everything together. So I'm gonna convert the 4 centimeters squared to 4.00. Okay, so let's start. So E is equals to, let's see, E is equal to hold on. The electric field is okay, it's right here, positive 1.20 times 10 to the negative 5. Oh yeah, and also I forgot to add the negative sign up here. I was supposed to add the negative sign. Yes, supposed to add the negative. Okay, so the negative sign. Okay, times 2 pi greater 0.0500, and then the mu naught is 4 pi over times 10 to the negative 1 Weber inches meters, and the 165 number, and the A is the area, which we know is 4 centimeters squared, so 400 times 10 to the power of negative 4. And I'm going to plug everything into the calculator. And that is going to give me the t is equals to negative 1.77 times A over second. Okay. So, so the reason, so the current is decreasing. So let me explain everything why. So the electric field is at like the point of the positive x-axis that points to the positive y direction. So using the right hand rule, if you use the right hand rule, basically it means that the electric field is clockwise, and so counterclockwise. So when it's a counterclockwise induced electric field produces a induced magnetic field in the positive z direction. So since the induced magnetic field is opposed to the change of the magnetic flux, according to the Lenz's law, the original magnetic field in the positive z direction must be decreasing. So because the magnetic field inside the solenoid is proportional to the current is also decreasing. So the answer is the rate of change of the current is negative 7.77 amperes per second, which means the current in the solenoid is decreasing.